We're on the air. Okay, it's Wednesday the 24th. We're doing variable separable equations and logistic growth. Take a look at number 6 on page 565 of the Harvard Calculus textbook, edition 4. Okay? What does it say? We have the growth of an animal population is governed by this differential equation. Can we solve this analytically? Let's see. All right, this is number 6 on page 565 of the Harvard Calculus textbook, just giving credit where credit is due. And we have 1,000 over p, dp dt is equal to 100 minus p. So this is a population growth model. It models the growth of a population of, I don't know, it says a population of individuals. I don't know, black bear in Yellowstone, okay, whatever. So where p is a population of individuals in the colony at time t, the initial population is known, it's 200 individuals. What did they just tell you? P of 0 is 200, initial population. Right, good. All right, sketch the graph of p of t. Will there be more than 200 individuals in the colony ever? Will there be fewer, and so forth? Now, that you can solve with a slope field. What I want to do, though, is go one step further. Can we actually variable separate this thing and get p as a function of t? Now, you're used to seeing dy dx, right? If it's not dy dx, pretend this is y and pretend this is x. So instead of finding y as a function of x, you're going to find p as a function of t. Okay? That's what we want to do. You didn't get one? Whoops. There you go. You didn't get one either because late fiend you? Yeah. Okay, so let's do it. Well, how would you separate it? Remember, it's only variable separable if you end up with a function in p times dp equals a function of t times dt. Right? So you can integrate both sides. Any ideas? What would you do to separate these variables, the p's from the t's? Well, let's be a little more specific. Divide and multiply who? Move the dt. In other words, multiply by dt. Okay. So. All right, one step at a time. Let's move the dt. Just to make it clear what we're doing. Go multiply both sides by dt. There you go. And you don't have to move the 1,000, but you're going to find that it's probably easier if you do. So I'm going to divide by 1,000. But I also want to get rid of this. This is not a function in t. I can't integrate it with dt, can I? So what are we going to do with this? And this? Divide also, right? All right, so you don't have to, but it'll become easier later on, so I might as well. dp over, I can't type today, or write, whatever it is. Okay. Over p times 100 minus p is equal to 1,000th of dt. Now both sides are integrable, aren't they? You can leave the constant multiplier inside the integrand or outside, doesn't matter. The question is, how do you integrate the left side? The right side's easy, right? What do you get on the right side? t over 1,000 plus a constant, right? Okay. What's that racket? Okay. That was weird. We don't usually get a racket like that. What is that? Okay, anyhow. So how do you integrate this? Any ideas? No?
ln.
No, not ln. That would be just a single p, like p to the 1 on the bottom. Anybody else? Ethan? This is partial fractions. Remember, partial fractions is not calculus, it's algebra. So let's go to the next page and do some algebra. I want to take the thing that I was integrating and make it easier to integrate. That was it, right? Yeah. By making it equal to what? How many fractions? This is called the decomposition method. We're decomposing this into 2 fractions. In other words, there's 2 fractions that you add them, when you add them by combining by getting common denominators, you can get this fraction, right? What would the denominators be? P and 100 minus p. So now Patrick is right. Imagine that. Is Patrick right now? You're going to end up with ln's, right? Because now it is p to the 1 in the denominator. And likewise here. All right, so we're going to make it an ln problem. It wasn't yet. So what happens up here? Well, not yet. Hang on. Not yet. You're jumping the gun. What do we need here? If this is first degree, this is 0 degree, right? What does that mean? Some constant. I don't know what it is. A p to the 0, if you like, right? What goes here? Huh? B? Right, same idea. Remember, if this is second degree, this would be first degree, ax plus b. If this is third degree, this would be second degree, ax squared plus bx plus c, and so forth. Yeah, I know. That's why I'm refreshing your memory for Friday's test. Now, why do you think we need partial fractions? Partial fractions comes up in logistics all the time. So if you want to solve a logistic equation analytically, you got to do it. Now, this is about as crazy a partial fractions as you're going to see in the AP, though. It's not that bad. We saw some really worse ones, right? Some crazy ones. This isn't that bad, is it? All right, so how do you resolve A and B? You need common denominators. So what's missing? Multiply top and bottom by 100 minus p. So I got 100a minus ap plus, what do you multiply top and bottom by here? P. So bp. And what must that equal? 1. Technically, 0p plus 1, right? Just to make the point, there's no p's. Why do I care about that? Well, if I have 0p, what do you know about a and b? I'm matching the p's, in other words. Well, they're equal, right? Negative a plus b has to equal 0. All right, negative a plus b has to equal 0. And what about the 1? 100a equals 1. Okay, 100a equals 1. All right, so do you need matrices here? Remember we did matrices with this stuff? Nah, this one's easy. Because a is clearly what? A is 1/100th, right? Just divide by 100? Well, if negative a plus b is 0, isn't a equal to b? So, guess what? We got b for free. Okay? All right, so why do we do all of that stuff? So we can integrate that. We're going to rewrite this as a over p plus b over p, but a is 100th. And b is 100th, right? All righty. So let's do that. Okay, I think I'm going to just fit it in here somewhere. Okay, so I'm going to write it as 1/100th of 1 over p plus 1/100th of 1 over 100 minus p, right? So I don't have the integral here, and I don't have the dp yet, right? But this is a over p plus b over p, b over 100 minus p. Now let's put the integrals back in. Now you can integrate. One thing though, I'd rather get rid of these hundreds. Can I get rid of them somehow? Yeah, multiply it through by 100 and you get a tenth here, don't you? All right, that makes life a little easier. Let's do that. So the integral of dp over p plus the integral of dp over 100 minus p is equal to 1/10 the integral of dt. There you go. Now it's easy. That's not easy. This is. Isn't it? You tell me. What's the antiderivative here? ln absolute p. But p is a population, right? So the absolute value doesn't really matter. It's always positive. Unless p is 0, then this is undefined. Okay, but if the population is 0, then you don't have much growth, do you? So we're not worrying about that. P's got to be greater than 0. So that's technically optional, the absolute value. How about here? ln of 100 minus p? Is it? Wrong. Why is it negative? Because if u is p, du is dp, you get ln u, absolute u, right? But u is 100 minus p. So du is negative dp. So replace dp with negative du. You get negative ln absolute u. And here we've got to worry about the absolute value. This could be negative. Equals, well, we said this part was easy. What do you get? T over 10 plus some constant. Technically, there's a plus a here, a plus b here. Combine them on over here to plus c. That's why they always say plus c. Okay? But you really don't need two constants. Just group them all together as one. Well, fine. We got rid of the derivatives. The integrals are done. But do you have p as a function of t? Combine the logs. How? What's the difference of two logs? The log of the quotient. So, you know what? I'm going to move to somewhere else. I'm going to run out of space on this when I print this out as a PDF. So it's going to be ln of p over 100 minus p. Let's go over here. ln of absolute p over 100 minus p equals 1/10 of t plus a constant. Okay. Now, can you get rid of the ln? E to the both sides? Is that okay? If you e to the both sides, what happens to the ln? Cancels. So you got p over 100 minus p. We never proved this, but the absolute value goes away too, by the way. Equals some constant times e to the t over 10. Is that okay? Well, there it is. Right? Because what is e to the t over 10 plus c? It's really e to the t over 10 times e to the c. It's just some constant. I'll call it d. All right, why don't we resolve the constant? How do you get d? Didn't they give you initial conditions? P of 0 was 200. So what goes in here? 200. Is equal to d e to the, well, what goes in here? 0. So e to the 0, that's just 1. So d is, there it is, that's d. Okay. So you have 200 over negative 100 is negative 2. Right? Is it negative 100 on the bottom? So 200 over 100 is 2, and it was negative. So negative 2 is d. So the general solution to that logistic curve is this. The general solution is, well, this. But is this done? Is this something you can graph? Like y equals f of x. I need p is f of t. How do I do that? How do I get p alone? I want to get p alone if possible. If I can, I can. Sometimes you get an implicit relation, not an explicit function. But can we get p alone? What do you think? Scrolling down, you mean? This is scrolling down. The paper's going down. When we plugged in 0, it went away, but it's back, right? Okay. All right, so can we get p alone? Again, this is just algebra. Yeah, we can. Yes, you can. How? Hint. I want to get p alone. Hint. When one fraction equals another fraction, what can you do? Cross multiply. So 1 times p, the product of the means, equals this times this, the product of the extremes. Okay, well, that didn't help. I want to get p alone, right? What are you going to do? Distribute. Okay, so p equals, let's see, let's distribute this over this. Negative 200 e to the t over 10. And a negative times a negative is a positive p, 2p e to the t over 10. Now what? Get all the p's together, right? So subtract this from both sides. P minus 2p e to the t over 10 is equal to negative 200 e to the t over 10. All right, how to get p alone? I'm still not there. Factor out p. 1 minus 2p e to the t over 10 equals negative 200. Oh, whoops, sorry. I factored out the p, right? That was the whole point. Okay. And t over 10. Is that good? And then divide by this and you got P alone. Good. So P equals negative 200 e to the t over 10 over 1 minus 2 e to the t over 10. And you have just solved analytically for the first time a logistic differential equation using partial fractions and variable separation. Yeah, well, we're going to have to because it's on the testola. All right, so now guess what? Nobody would write the answer this way. Hal wouldn't write this. Bob wouldn't write this. I don't like this. What if I factored out a negative top and bottom? Yeah, I know. I'm just saying, what if you want to compare this to Hal? It's not going to look like what Hal says. Hal doesn't say that either. Well, Hal might say this, but Bob wouldn't say this. You know what Bob would say? Back of the book. You never consulted the back of the book, checking your homework on the odds? Okay. Bob does this. Look, I don't like all these e to the t's. How about if I divide everybody by e to the t over 10? Divide the top by e to the t over 10, you get 200. Divide the bottom by e to the t over 10, you get 2 minus e to the negative t over 10. And just a simpler form of the same equation. Okay? All forms will look the same when you graph them. They're the same solution. All three are fine. So if you stop here on the AP, no one's going to kill you. Right? This will give you full credit if this is an AP question. Free response. But this is easier to deal with if you have to substitute stuff or if you have to graph it or whatever. Let's graph it. Let's see what Hal says about this. All right, Hal, wake up. You've been sleeping long enough. All right, what mode am I in? I am in function mode. Good. So let's go to y equals and graph this crazy thing. It's 200 over, open parentheses, 2 minus e to the negative t. Well, I'm in function mode, so I'm going to use x over 10. Close the e to the, close the denominator. And if I do a zoom 4, I don't see a hell of a lot. Why not? Yeah, because remember, the initial condition was at t equals 0, you had 200, right? So I need to see that. And notice the growth rate here was positive. I think it's increasing as t increases. It's a logistic growth model. So I need to see p or y equals 200 to y equals, I don't know how big it gets. Do we know how big it gets? Well, I think we do. If you get dt alone, if you move p over, when is dp dt 0? When p is 100, or if p was up here, multiplying, p was 0. Those are the equilibrium solutions. P equals 0 and p equals 100. Remember logistics? There's usually two equilibrium horizontal asymptotes. One where they run away from, it's unstable. One they gravitate toward. It's a stable equilibrium. I think it's trying to get to 100. It started at 200 and it's trying to get to 100. So this is a logistic decay curve from 200 to 100, I think. So I need to see at least up to 200. So let's change the window. Let's go from, do we need negative time? Nah. Let's say 7.9 days or weeks or whatever the units are. That's fine for now, I guess. And then I don't need negative black bears, do I? So let's go up to at least 200 to see the initial condition. And maybe a 10 here just to see some tick marks. All right, let's see what that looks like. There it is. It's a logistic decay curve. If the initial condition was less than 100, like 10 maybe, it would have been a logistic growth model, that weird thing with the concave down, and then horizontal asymptote at 100, right? Huh? What is the limit? You tell me. It's got to be 100, sure. Let's change the window, make it, I don't know, make it 100 weeks or whatever the units are. Does it look like it's approaching 100? Remember, this is 0 for P and 200 for P. That's right in the middle, isn't it? Looks like it to me. If you don't like that, you could always put in the 100 here and see if it's an asymptote. Looks like it to me. Notice how this is going to fit the slope field perfectly. Take a look at the slope field. Go to mode, change from function mode to diffeq mode. And now it's, yeah, I don't want that one. Let's change the function, the slope field that we're doing. To what? Well, I got to write dp dt alone, right? So p is y1, and t is, well, t, right? Remember, they use t here. So how do you write dp dt alone? How do you write y1 prime? It's 100 minus p, what? Times p, and divide by 1,000, right? Okay, so you know what? I'm going to write the 1,000th in front just for the heck of it. Times the 100 minus p, which is y1, right? And times y1 again. Now, I forget where it needs explicit multiply, probably here, right? Is it happy with that? Yeah. All right, and let's put in the initial condition even. At t equals 0, you started off with 200 creatures. And notice I didn't change the window. Right? Or did I? That's weird. How come the window doesn't usually change when you do this? All right, I'm going to put the window back to what it was. We went from here t and x are the same thing. So t equals 0 to 100 weeks or something, I think we said, right? And p equals 0 to 200. Black bears or whatever the heck they are. And time, I think x and t are working the same here. So I'm going to go from 0 to 100 here. And 10. Well, t step, All right, let's see what a graph's like. Here's the slope field. Does it look like you have a horizontal tangent at 100? Sure does. And it's starting at 200, and does this look like the same function? Now remember, Hal is just approximating the solution curve using Euler's method. But it's coming up pretty much with the same curve we just got analytically, which was exact. So Euler's method is very useful, especially if you can't variable separate. Any questions what's going on here? What if I put on ludicrous speed? And there you go. So the limit is 100 black bears or something. Okay? But what if I change the initial conditions? What if I started at t equals 10? What's going to happen? Instead of t equals 200. I'm sorry, p equals 200 is what we had, right? Let's start with p equals 10. What do you think you're going to see? And it went to sleep again because ludicrous speed is ridiculous. No, not that. What are you going to see if I start at 10? You're going to get that logistic curve. It's sort of like that S shape, right? Let's see. Change the initial condition to when t is 0, y is, I don't know, 10. Something between 0 and 200, 0 and 100. And there it goes. And it's going to be a little slow with that t step, so I'm going to speed it up. And there it is. All right, so that's a typical logistic growth curve, and before we had a typical logistic decay curve. All right? Now you know all the differential models that come up on the AP all the time. Exponential growth and decay. Exponential approach. In other words, we're decaying to a non-zero y value, like Newton's law of heating and cooling. And logistic growth and decay, like we just did today. All right? So now you guys are smart. It's about time. Any questions how logistics works? Any questions on variable separable? Any questions on partial fractions? All right, you're so smart, we're on the second side, or the other side of the page. All right? Okay, the other side of the page is just practice with variable separable again, because that's all we did today, really. We didn't do anything new. But these don't involve partial fractions, I don't think. All right? So how about, okay, let's start with, I'm on page 539. Let's start with, say, 17, just for practice, okay? All right, so let's get back into here. Let's get to another page. Whoa. And here we go. So how about 17? Can you solve this by variable separable? That's all this is about. Okay, dm dt, this could be like money over time or something, right? Equals 0.1 m plus 200. And your initial condition is m at times 0 is $1,000 or something, whatever it is. Can you solve for m as a function of t? Well, this is easy to separate, isn't it? Or is it? How would you separate this? Divide by this to get the m's with the m's, and multiply by this to get the t's out of the way. Okay, so dm over 0.1 m plus 200 is equal to dt. That's fine. But this is going to be a pain when you do u sub, right? Well, all right, let's do it. Who's u? If u is 0.1 m plus 200, who's du? What is it? 0.1 dm. So replace dm with, this is 1/10. So dm becomes what? 10 du, right? That's a mess. I don't know if I like that. All right, we'll carry that through, and I'll show you a different way in a minute. All right, so I'm going to replace dm with 10 du's, so it's 10 du over u. What's the integral of 1 over u du? ln absolute u, right? Okay. That was u, wasn't it? Equals, this is just u sub, man. This is your favorite u sub. You brought it up a minute ago with ln. Equals what? What happens here? T plus a constant. Okay. Can you get rid of the ln? How? First get the 10 out of the way, and then you can e to the, right? So I'm going to say that's ln absolute 1/10 of m plus 200 equals t over 10 plus some other constant, whatever it is. I don't care that it's a over 10. I just care that it's a constant. Now, how to get rid of the ln? E to the. So e to the both sides. And you get what? 0.1 m plus 200 equals c e to the t over 10, right? Remember, this is just another constant. E to the b times e to the t over 10. All right? So can you get m alone? Or can you get c? I don't care. You want to get c first? The initial condition was what? You start with 1,000? I think we could probably do that. So what do you plug in for m, and what do you plug in for t? M is 1,000, right? So what's 1/10 of 1,000? 100 plus 200 equals c e to the 0. So that's just c. So what's c? C is 300. Okay. So our general solution is this. Our particular solution is this. Oops, let's stay green. That's a 3. Because we divided by 1,000 somewhere. What the heck was it? I forget. We divided by that somewhere. Which where? Oh, this 10. Well, because du was 1/10 of dm. So we're replacing dm with 10 du's. How do you get rid of 1/10? I'm trying to replace dm with stuff and u. That's how we do u sub always. Always did it. What's the m? Well, if this is 1/10, how do you get rid of 1/10? You multiply by 10. So this is really 10 du's. Okay. Good question. Yeah. All right, so let's get m alone. We didn't get m alone here. How would you get m alone? Subtract 200. So 1/10 of m is 300 e to the t over 10 minus 200. How do you get rid of the 10th? Multiply. So m as a function of t is 3,000 e to the t over 10 minus 2,000. These probably might be easier to do the u sub if you factor out the 0.1 to start with. If you factor out 0.1, you have m plus what? Remember, factoring is dividing. When you divide 0.1 into 200, you get 2,000. So it would be easier to keep the 1/10 out of the way and have m plus 2,000 here. So then the du would be m plus 2,000, and du and dm would be equal. It would be easier to deal with. But this works out. I mean, the u sub always cleans it all up for you anyway, so you would end up with the same thing. All right, just practicing up. How about, all right, how about 19? Ready? Here we go. Okay, 19 said dB dt plus 2b is equal to 50. Can you separate the b's from the t's? Any ideas? Got to get it to a point where you can probably like factor out stuff, so you can divide stuff, and you get b as a function of b with db and a function of t with dt, and the function could even be a constant. And Ethan says, okay, so dB dt is equal to negative b, 2b plus 50. All right, now what? Cross multiply. All right, so dB equals negative 2b plus 50 times dt. All right, but what did we say a minute ago? Wouldn't it be nice if we just had b? You don't have to do this. The u sub will clean it up, but the u sub will be harder. Can you factor out this new negative 2? Can you get rid of it out of the way? Factor it out. What do you get? Negative 2 times what? b minus 25, right? Because if you're dividing both sides by negative 2, this becomes negative. All right, now you separate it further. How? All right, so now this becomes easier to integrate. If you didn't factor out the negative 2, it's a messy u sub. It's doable. It's not a big deal. But this is probably easier to deal with. So we have a function of b dB and a function of t dt. The function could be a constant. That's fine. And can you integrate this? Isn't this a straight u sub? Who's u? b minus 25. So who's du? dB. This is 1 over u du already. So what do you get? ln u. There it is. Equals what? Negative 2t plus a constant. Okay, now what? E to the? Okay. So you got b minus 25 equals? Yeah, that's unfortunate, isn't it? All right, I'm going to go to c. E to the negative 2t. I would have done b, right, usually, but that's not a constant. That's a variable in this problem. All right, so c is a constant. And so to get b alone, you just add 25, and there's your general solution. B as a function of t is 25 plus c e to the negative 2t. But did they give you initial conditions here? B of 1 is 100. So b is 100 when t is, it's 1, right? So e to the negative 2. Plugging in 1 for t, right? So it's 1 times negative 2 is negative 2. All right, can he get c alone? Subtract 25 and divide by e to the negative 2. But e to the negative 2 is already in the denominator, e to the 2, right? Just like multiplying by e to the 2. If you divide by e to the negative 2, it's like multiplying by e to the positive 2. All right, so put that back in place of this, and you got b minus 25 is that e times negative, wait, didn't we get b alone? There. I'm going to put that in place of c, right? So b is equal to 25 plus 75 e to the 2 times e to the negative 2t. No one writes it that way. Can't you combine these two e's as one? 2 powers of e is 1 power of e? All right, so I'm going to say b of t is 25 plus 75 e to the 2 minus 2t, all in the exponent. You could do that too, same thing. No, those are not like terms. You can't. No, don't get crazy. All righty, and we're close to being out of time, are we not? Okay, you should be able to finish this sheet on your own. I would say, there are marks on your paper, right? The multiples of 5? Yeah, that's homework. Okay? So 5, 10, 15, 20, 25, 30, 35, 40. Okay? You should be able to do all of those by variable separable, and I don't think you need partial fractions for this. All right? There you go. That's all she wrote.